Hey everybody! Today is going to be a nice short lesson. We're going to talk about how to do derivatives of trig functions. So those of you who are sick of polynomials and the product rule and the power rule and the quotient rule, we'll look at some different types of functions. And remember, it's kind of our objective for the next few weeks anyway, to take a look at all the basic functions we know about and learn shortcut rules for finding the derivatives so we don't have to use that limit definition over and over again. Now, today is going to be a shorter lesson, so as to save a lot of time towards the end of class for you guys to work on the quiz. So hopefully you guys are ready for that, and so you guys will do that in the second half of class today. Okay? So as I said, today we're going to look at how to find derivatives of trig functions. It's actually a pretty easy topic, but it's going to give you some more formulas to memorize on the other hand. So let's start off with the sine function. One of our basic trig functions. Let's say we want to find the derivative function for the sine x function. Now I'm going to actually prove this for you later, more formally, using the limit definition. But for right now, to make it quick, let's actually just have the calculator graph the numerical derivative graph, and hopefully we can recognize it as something familiar. Okay, so if you want to play along with me here, I'm going to graph the sine x function. You have to make sure you're in radian mode or this is not going to work. Okay, so make sure you're in radians. And I'll just push zoom 7, zoom trig. And so obviously this is what the sine function looks like, the regular old sine function. Now what I'm interested in is what does the derivative of this look like? Now we could sketch it because we know that wherever this has peaks, like right here, the derivative should be 0, right? Because it comes to a horizontal tangent. So right here the derivative is 0, right here the derivative would be 0, right here the derivative would be 0, and right here the derivative would be 0. Okay? Also, in the interval like between these 2 points, let's say, the function is increasing. So that means it has a positive slope, which means the derivative is positive. So the derivative, no matter where it is, it's going to connect the dots, but it's also going to be positive the whole way. So we maybe sketch something that looks like that. Between these two dots, the function is decreasing, so we would expect a negative derivative. And between these two dots, the function is decreasing, so we'd expect a negative derivative. So that's what we would expect to see. So let's go ahead and draw that in. We'll use the numerical derivative command. So math 8. So nderiv, and I'm just going to go ahead and put y1 there. So it's just going to take whatever's in y1 and find the derivative of it. Comma x, and then for a graph, we'll put comma x again. Okay, I'm going to graph this in bold, so as to differentiate it. So here we go. Slowly but surely, it's plotting the numerical derivative at every point along the way, and it's graphing pretty much a good picture of what I sketched earlier, of what we would expect the derivative to look like. Okay, now if you focus in on this function in bold, that should be a familiar function to you. And in fact, that function is, you know? You got it? Cosine x. Cosine x starts up at 1 and does 1 cycle. So, informally at least, we've got some evidence suggesting that the derivative of sine is cosine. Now I'm going to do the same thing with the cosine function. So let me go back here. I'm going to change my first function to cosine x. And turn the second function off real quick. So here's the graph of the cosine function, as we just saw. And again, if we wanted to sketch out what the derivative would look like, we would put zeros where this graph has peaks, and it would be negative wherever the graph is decreasing. So you can kind of maybe you can maybe visualize what the derivative graph would look like. So let's actually plot it up there. The numerical derivative looks like this. The question is, what function is that? Well, it's not sine, because the sine function looks like this. So how's that bold graph related to this green graph I drew in? Because the green graph is y equals sine x. So how's it related? Yep, you're right. It's the negative. So this graph right here, this derivative graph, is negative sine x. Okay? So we've got some evidence to suggest that the derivative of cosine is negative sine. Again, we'll prove that a little bit later. All right, so let's just write that down in our notes for right now. Actually, I'll go ahead and just do this real quick. Okay, so one derivative rule is that the derivative of sine x is equal to the cosine x. And the second rule we discovered was that the derivative of the cosine x function is the negative sine x function. Okay, so there's two. And now we can actually, that expands expands all the problems that we can do with derivatives, because now we can add in cosine and sine to those. Especially what we're going to be seeing more of now are mixtures of regular polynomials with trig functions, which are going to necessitate the use of product and quotient rules. So let's look at an example real quick before we move on to the other trig functions. Let's say we're given the function x squared sine x squared times sine x. Unlike some of those other product rule problems we did before, where you actually had the choice of multiplying it out first before you did the derivative, you really don't have an option here. There's nothing you could do to simplify this in any way. So the only way to differentiate is to use the product rule. Okay? And now that we know how to take the derivative of sine x, we can incorporate that into the process. So my derivative, y prime, using the product rule, we go first function times the derivative of the second, derivative of sine, cosine, plus the second function, sine x, times the derivative of the first, which is 2x. Okay, and then we'll just simplify it. In this case, there's not much we can do. I'll call it x squared cosine x. Usually we write the 2x part in front. There's really not anything else I can do to simplify this. So that is the expression for the derivative of that function. Okay, pretty simple. Similarly, we could do a problem that requires the use of the quotient rule. So let's say I have a function that looks like cosine x over 1 minus sine x, let's say. Let's say I want to find this derivative. Well, now I'm forced to use the quotient rule, because again, there's nothing I can really do to simplify this and put it in any other form. So let's find the derivative. We'll call it dy dx this time, so I can use the other notation once in a while. So for quotient rule, we have to take the bottom function, 1 minus sine x, times the derivative of the top, derivative of cosine, is negative sine, minus the top function, cosine x, times the derivative of the bottom. And derivative of 1 is 0. There's going to be a negative. The derivative of sine is cosine. So the derivative of 1 minus sine x is going to be negative cosine x. All over, don't forget the denominator part. It's a common mistake. Sine x squared. You get so excited doing the numerator that sometimes you forget that denominator squared part. Okay, so let's just simplify a little bit here. I'm going to distribute that through. So that's going to give me negative sine x plus sine squared x minus, and this product would be negative cosine squared, so I'm going to make it plus cosine squared x all over. And again, keep the bottom in factored form. You don't have to FOIL that out. It's not necessary. However, look at what happens in the numerator. Hopefully you see that or hear that. If you were in my class last year, you know about hearing the trig identities calling out to you. Hopefully you hear the sine squared plus cosine squared calling out to you, because that's equal to 1. So sine squared plus cosine squared